Okay, you're welcome to the first chapter of this course, which is Introduction to Speech Processing. Most of the notes for this book is taken from the book by Rabina, and a lot of additional things I have put in, but having said that, that's the reference book for this particular chapter, and you are encouraged to read the book. You get a lot of information. So what is speech processing? We look at that, and then what we see, what sort of application you have. Speech processing. The main application, I have listed a few applications here for you. Speech coding. What is speech coding? You take the speech signal, which has got a lot of redundancy, and you can compress them in a CD. That's basically compressing the speech is called speech coding. Then speech recognition, recognizing a person, speaking to the computer, or typing a letter. You want a computer to type a letter for you while you're speaking, so it understands you. Either it's an isolated word or continuous word, so that's all speech recognition. Speaker verification system is in front of a computer. You go and speak to the computer and looking for the computer to give you to verify you as a claimed speaker. So is security applications like banking and accessing a big database, you need that particular application where speaker verification is done through a computer. And speech enhancement. What's a speech enhancement? For example, you've got a background noise. For example, using a mobile phone in a moving vehicle, you've got a background noise. You want to remove that noise before you send the signal across to the receiver or person receiving the signal. So that means you need to have a speech enhancement chip inside the mobile phone, which will remove the noise. So that's speech enhancement. Then you come to speech synthesis, which is basically text-to-speech synthesis, the major one, and where you type into the computer and the computer speaks to you with a high-quality speech. And still it's early stages, not really advanced, even though there are advanced algorithms available, but you don't find really high-quality speech synthesis system available. Okay. So in order to understand speech analysis and speech processing, first you need to understand speech processes and then how the speech is produced. Then once you get the waveform, how do we analyze them? Basically, let's look at the figure, which is in the next page, which I'll look at in a minute. And speech production process. Basically, if you want to say something, it starts from your mind. You first decide, you first formulate the message in your mind, what you want to say. So once you have formulated the message, you then decide what language I'm going to say. So the next step is to create a language code, a text message or message you have thought about it. Say, for example, you want to say hello in English or in German. If you know both languages, you will create the code accordingly. And once you have created the code, then the next step is you want to start to move your muscles and trying to move your vocal apparatus to say the word. But what's the language code? For example, in speech, the smallest sound is called phoneme. So, for example, here I've mentioned here phoneme. Phoneme is a sequence of small sounds. And for example, in English, there are 45 phonemes. And you put the phonemes in the correct order, you get a word. And if you put them in the wrong order, you get a nonsense word coming out of it. So similarly here, you have learned when you were small how to put these phonemes in the correct order in order to say a word. Okay. Once you have done that, you have to decide what's the duration of the word. Are you going to say hello, or are you going to say very quickly hello? So if that's the duration, you want to work out that. Then you want to decide how loudly you want to say. That's also you decide. And then you decide what sort of pitch you have to associate with. That's the vocal cord vibration. Do you want to say in a normal way hello, or really in a tense way hello? So you work out the pitch what you want to say. All these are worked out before you start to move your muscular or the movement of your muscles. Before you do that, you have all these thought out. So quickly you do this. So if you look at the speech and generation block diagram, first message formulation. You have formulated the message. It could be text, you thought about it. and you have formulated. Second one, you have created a language code because you have decided what code is. You have selected the phonemes requested for that particular language. And these are discrete out input, very small data. And then once you have decided, you will start to control neuromuscular controls. You're going to move things. Which one you want to move? You want to move your jaws. You want to move your tongue. You want to move, your vocal cord has to vibrate. So the muscles have to start to move. And you then control your vocal tract system in order to say a word hello. So you get a speech waveform coming out of here, something like that. And that speech waveform, if you sample them using an A to D converter here, you will find it's something like 64 kilobits per second. That's the normal bit rate. That means 8 bits per sample, 8 kilohertz sampling rate, 8 times 8 is 64 kilobits per second. And that's available here as a discrete time waveform. So these are all discrete, here look, and then you move into analog because these are all moving continuously, and what's coming out is analog, but you want to use a computer to process it. That means you need to use an A to D converter here to convert this analog waveform into discrete waveform. So you have here discrete waveform here. So discrete waveform comes to the receiver, which is the ear. So what does the ear do? It is a spectrum analyzer. It analyzes what sort of frequency is available coming out, and it analyzes that. So that's the basilar membrane motion, we call it, but we don't want to look at it now. And once you have analyzed this, look at the spectrum analyzer output, and then you extract features from it. What are the features you will extract? The features are, is the vocal cord vibrate for that sound? What sort of intensity is coming? What sort of duration of the sound? And then you work out which frequencies are really resonating. Because the vocal tract, in order to produce one sound, will resonate at various places. So you will see, if you look at the spectrum here, you will see, I'll just throw it on this corner, that's frequency, that's amplitude. You will see for a voice speech, like spectrum light. So you've got a peak here. You can see here there are peaks here. These frequencies are enhanced. So different frequencies are enhanced. So this neural transduction block inside here, after the ear, gets all these features. And these features are coming continuously, so they are continuous output. Then, using those features, you decide, you do a language translation. And if it's English, you do English translation to phonemes. Or if it is German, you go for German language phonemes. And that's then passed to this message understanding block in the brain, which then interprets, yes, that person said hello. So I must now say to him, how are you, for example. So that process continues. You understand, then you start to say, you formulate what you're going to say. So this loop continuously doing it. You can see, if you now concentrate, I just dropped this out, if you now concentrate, for example, very carefully, see the bit rate, what sort of bit rate we have. Let's have a look at the bit rate. So if you look at the bit rate, you see here, you started with a 64 kilobits per second, and you came to 2 kilobits per second. So you have removed a lot of redundancies. Then from that, because this is a discrete input, so you've got 200 bits per second. And then, to understand the information, you only need 50 bits per second. 50, 200, 2000, 64, and so on backwards. So basically, in order to understand a word or a smaller sound, basically 50 bits per second is more than enough if you have it. So that's the block diagram of our system production. So I have already explained all these parts using the diagram, using the figure. I've talked about it, so you might just read through them and see whether you understand. Again, the same thing, same diagram. I just want you to concentrate. most of the thing that we will be doing in speech analysis is looking at that part and looking at that part, how do we process them. We do not concentrate on that in our process. We will be trying to model vocal tract. So assuming signal is coming here, well, movement, and we will learn how to model the vocal tract, how to produce the speech. Once you produce the speech waveform, how do we analyze them? We can model this and analyze them, or other ways of analyzing as well. So we will learn that. So this is also part of your work, and this is also part of your course. Without doing this model, full model, we can use other models from the speech waveform as well, which is good enough to this, but they're not exact physiological model. Okay, so the main part of the course is going to be there, and here analyzing and using these two techniques. That's the way the course is designed. And if you are interested in actual physiologically how the basilar membrane works, and there's a lot of modeling available, and you can spend, basically if you're doing a research in a Master of Engineering Science or ME or PhD, you can actually spend time on these, how to model them. Okay. Again, all these things I have already mentioned, how the process works. I mentioned that. I mentioned already. I have also mentioned this. So if you have understood the diagram, the figure, then I don't think there's any problem then. And we have just talked about the information rate. That is how much information that the rate that you have to have when you're processing in the brain. At the analog level and the acoustic level, you need high information rate. That is 64 kilobits per second. As you go along through the ear and process them and further process them and so on, so on, so on, when you move in, the information rate decreases, something like 50 bits per second you need, so very low. It's not a very high processing inside. There's very low rate. As you all know, but the brain has got like trillions of neurons, and they all work in parallel, but very slowly. And that's why the bit rate inside the brain is, we're talking about like 50 bits per second. I've already mentioned that. And but at the acoustic level, it's a high bit rate. At the neural level, it's a very low bit rate. Next thing that we are interested is, I've just talked to you how we produce. Next thing, we have to look at our vocal apparatus. And we want to model. We want to write equations and see how we model the work, so that then we can write transfer function on all sorts of things. So we're going to work out the mechanism of speech production. How am I producing the speech? How do I move my articulators? When do I open my mouth opening? Sounds like M, we close the two lips. Sounds like O, we make a round here. So when do you do them? So depending on the sound. So the model has to accommodate everything, all the sounds. So we are going to look at our speech production. So in order to apply DSP technique in speech, it's important to understand how the speech is produced. That's important. You need to know how it's produced. So we know the speech signals are composed of a sequence of sounds. As I said to you, the basic sound is phonemes, so they are composed of many sounds. And these are produced, these sequence of sounds are produced by acoustical excitation. Excitation happens here at this point. So why do you have to have excitation? For example, in English, there are two types of sounds, voiced and unvoiced sounds. So for voiced sound, like it sounds like ah, the vocal cord at that point vibrates. Ah, if you say that, you can see a vibration. You can hold two fingers here and try to say ah, and you can feel the vibration. But a sound like unvoiced sound, like sound S, if you say and hold it here, the vocal cord does not vibrate. The air is pushed across and just comes out and is shaped by the vocal tract and comes out as a speech, like a noise. So there's two types of sounds. They are the two major sounds we have, and there are other categories, but you can distinguish them. So basically the air is expelled from the lungs through the vocal tract here right, through at the vocal cord, and then the sound is traveling through the vocal tract and at the lips, okay? So let's look at this diagram. So the vocal tract begins the opening between the vocal cords and the lips. So there is the lips, there is the vocal cord in here. So the vocal tract is basically this tube. This tube that you're talking about, that's the vocal tract. About 16 centimeter long. And it's an acoustical tube of different diameter. So if you look at the diameter, it will be like that. If I don't approximate them like that, like it could be like that, it could be like that. Sorry. And the diameter is like that, okay? So it's an acoustical tube. Now, you find that in the average male, the vocal tract length is about 16 centimeter. The cross-sectional area, that's this area, like cross-sectional area there, cut across. You can see, if you cut across, you will see the cross-sectional area. For example, give me a second. So you'll find, if I just cut there, the area here is different. It's larger than the area here. Like so, that's the cross-sectional area of the vocal tract. Determined, how do you determine? It's determined by the position of the tongue, like tongue position, lips and jaw, and the velum. Velum is the soft part connecting with the vocal tract and the nasal tract. For example, you can see in this diagram, where is the velum? So you can see here, velum is here, this part. Sorry, that's not the part, this part here. So vocal cord vibrates, so you expel air from here when you want to say a sound, and air comes through this, through vocal cord vibration, and then it comes through this, and when it comes, if the voice sounds like ah, it's directed through this way, and you get the sound coming out. And if it's an unvoiced sound like a, and a nasal sound like a you close the lips and let the air to go through. So for a sound like M, and the air goes through this and comes out of the nostril. Oh, it's just above cavity. Sorry. Let me draw it again. So it goes there and comes to the nasal cavity. Okay, for sound like M. So it's important that different sounds are produced. So vocal tract and nasal tract. There is a soft palate moves up and down to couple the thing. And the nasal tract, you look at the nasal tract, begins at the velum and ends at the nostrils. So velum is here, starts here, and goes to the nasal cavity. That's also different diameters, and ends up there. Okay? When the velum is lowered, when you lower this, when you slow down, the nasal tract acoustically coupled with the vocal tract. So the vocal tract sound, the air coming through this is acoustically coupled and sent through that in order to produce nasal sound. So as long as you know, there are like three categories simply. Voice sounds like ah, vocal cord vibrates, sounds come through this, through the vocal tract, comes out of the lips. Sound like S, where vocal cord does not vibrate, air rushes through and comes through the vocal tract out here. They have different spectrum. Then you go for sound like M, where it comes from here, and then the soft palate is closed in the vocal tract and allow the sound to come through the nasal tract. They're the kind of three types. So when you classify the speech sound, how do you classify speech sounds? Sounds are classified in two modes: voice sound, unvoiced sound. That's the basic classification. Voice sound, vocal cord vibrates. Unvoiced sound, vocal cord does not vibrate. Sounds like S, F, vocal cord does not vibrate. So if you actually can measure the glottal volume velocity, the air coming here, and if you can measure the velocity in time, when for a voice sound, vocal cord closes, then open, closes and open. If you hold it, you can feel the vibration. It's closing and opening and closing and opening. So you can see if you measure the volume, there is a distance between that. That's called the pitch period of the vocal cord. Vocal cord vibration has got a particular pitch period. And you will find the vocal cords vibrate at a particular frequency, which is called the fundamental frequency for a particular person. And for male speakers, that frequency, if you measure it between 50 and 200 hertz. For female speakers, it falls between 150 and 300 hertz. For a child speaker, and that's the range. So basically, if you measure this distance, and this is T, then your frequency, fundamental frequency, is 1/T hertz. And that's what I have given you. So roughly, you've got an idea. So you know when somebody is speaking on the phone to you, without knowing a person, you ring somebody answers it. As soon as they answer, you say, there's a child speaker. How do you know? The child speakers, from pitch, they normally fall very high pitch. From that, you can say. Sometimes you are confused. No, it's not it's a female speaker, but I don't think it's a child. Because the age difference, you can see when it's a child, the pitch is going to be very high. When the person becomes, getting older and older, the pitch goes in this region, like 150, 200 region. So it's very hard to know the overlap region. There's a child or actually adult speaker. For male speaker, it's reasonably easy. You can distinguish between a male and a female speaker or child speaker very easily because male speakers have got between 50 and 200 hertz, which is reasonably separated away. It's a low frequency vibration of the vocal cord. So that's how you really normally identify a person. From their pitch, from listening to the pitch, there's a male speech. You've already trained yourself when you were small. You've stored all the information to identify, classify male, female speakers. Having said that, there are cases of overlap where it's very difficult to know whether it's a male speaker or female speaker and at the overlap. So look at unvoiced sound. Now we are looking at unvoiced sound. And if you look at the unvoiced sound, what happens is if you measure the frequency spectrum, it is characterized by high frequency component. That's the characteristic of the unvoiced sound. Voiced sound is low frequency component. Right. Now I will show the spectrum in a minute. Okay. For the moment, you can think it's so for unvoiced sound, the vocal cords are held apart. The air rushes through the lungs, through the vocal tract, shaped by the vocal tract, and comes out at the lips. Other sounds, you've got other sounds, nasal sounds. I've told you that vocal tract is coupled acoustically with the nasal cavity, and sounds radiated from nostrils are M, N, Ng. If you say Ng, is an unvoiced sound. Plosive sounds, which also another type of sound, where you build up a pressure first and then release it abruptly. For example, a sound like P. What will you say? You hold P, you build up the pressure behind the closure, and then open up. P. So you suddenly open up. That's a different type of sound, okay? Which is called plosive. Easily identifiable in a speech waveform. You will learn that in a speech waveform. You can look at the speech waveform. You say, that's the voice part. That's the unvoiced part. That's the plosive part. It's easy to say. You will learn that part of the course. So the next thing we are going to learn is the vocal tract, which is like an organ tube, different diameter, different length. But 617 is the length, but different diameter. So diameter here, if I want to say a sound like the diameter here, diameter here, diameter here is different. Okay, so what happens is the vocal tract, what we call is a non-uniform acoustic tube, starts from at the vocal cord and ends at the lips. The cross-sectional area of the vocal tract is determined by the position of the tongue, lips, jaw, velum, and depends on the it's a small error there, don't worry. It depends on those position articulators. If I just say a sound like P, is a different diameter. If I say a sound like different diameters. So when you have different diameters for a tube, you will have different resonance frequencies. And those resonance frequencies are the one is normally analyzed by the ear and determined by the brain as a features for that particular sound. So if you can't identify those frequencies, then you start to get confusion. You don't know whether I'm distinguishing two sounds. So in order to distinguish two sounds, these basic sounds, basic phonemes, you need to pick up all these formants frequencies or resonance frequencies. These resonance frequencies we call format. So basically, resonant means what? You have a graph, here is a frequency versus amplitude. So if you want a resonant, it means get a peak there, and so I could say in this particular sound, I got a one frequency F1, F2, and I got F3. I got three frequencies. I have got the all resonant frequencies. So normally, you will find by lot of tests we have found that every kilohertz you will have one resonance frequency. If you are talking about a bandwidth of 4 kilohertz, then you will have four resonance frequencies. Now, when we come to bandwidth, I'll explain to you a few other things now for you in a minute. So 3 to 4 formants are present below 4 kilohertz of speech. So now you have a question. Telephone speech, what's the bandwidth? Telephone speech is 4 kilohertz, 0 to 4 kilohertz is the telephone speech. That's I'm too fast. So you can say 4 kilohertz is the bandwidth, 0 to 4, and it's telephone speech. Telephone speech. But the next question is that what's the actual bandwidth when you speak? When I'm speaking and when you are hearing, we are talking about a wide band. That means speech, if you measure all the frequencies in speech, you get about 7 kilohertz. So you are actually hearing 7 kilohertz bandwidth. But over the telephone, we filter them and keep it as 4 kilohertz so that you can sample at 8 kilohertz. Okay? For wideband speech like ISD and link, you must have the wider bandwidth. So formant frequencies, we are going to look at the formant frequencies. There are 3 frequencies I told you is very important to distinguish the sounds. What are formant frequencies? Let's have a look at a diagram. We're going to show for voice speech and also unvoiced speech the formant frequencies. So let's look at the diagram. Through the diagram I can explain to you. Have a look at here. I have now modeled a small block diagram of my speech production models. What's the block diagram? There are 2 major sounds, voiced, unvoiced. When I want to have voiced, I get my vocal cord vibrate. So that's the vibration. And that goes through a small amplitude controller because most of the time, voice sounds has got a higher loudness, higher intensity, as opposed to that's the unvoiced sound, very low intensity or power in it. So we need to have an amplitude control. We need to switch between voiced and unvoiced. It is voiced, you get the vocal cord vibrate. Unvoiced bit, you keep it held apart. So it doesn't. So you decide. You have a soft switching them. Then you come to your vocal tract, which is a filter because it's producing resonance. So it's a filter with a variable resonance frequency. It's time-varying filter. You cannot have vocal tract fixed shapes because then you will only produce one sound. If I say a sound all the time, then I'm keeping the vocal tract fixed. So if I want to say something, communicate with you, you can't keep it always fixed. You must vary. You must vary the shape. You must vary the resonance frequency. Then only you can produce a sound. Okay? So it's important for you to move, articulate it. If you look at the voice speech, it looks like this, and unvoiced looks like this, for example. And we look at further. So let me look at that point, what is the spectrum at that point? If I get equal pulses separated at equal distance, the spectrum will be decaying like that at 2 pi over t. So it has got a fundamental harmonic, second fundamental harmonic, second harmonic, third harmonic, and so on. And then your vocal tract here has got a resonance frequency. At one time, it's like this. You look. For voiced frequency is high at the lower end and lower. So it has got a lot of high energy at the low frequency end. And when you multiply these two together, then you get this spectrum there. So if you look at, then if you take this spectrum, multiply that spectrum, frequency domain, you then have got, this is your output spectrum. So that's what the multiplication is showing. You have done that. If you have got cascaded system, in time domain they convolute, in frequency domain they multiply. You take a noise generator, take the spectrum of that now. It will be flat spectrum because noise is, has got all frequencies, equal amplitude. All frequencies, equal amplitude. Then the vocal tract shape is such that for unvoiced sound, it enhances the high frequencies. Here look, its amplitude higher and suppress the low frequencies. That's how brain works out. Okay, I'm getting this pattern, that must be voiced. I'm getting this pattern, it's unvoiced. So that's how you classify. So you must know the spectral plot for voiced and unvoiced. You must know that. These points, that one, that one, that one, are called the four-man frequencies, F1, F2, F3. Similarly, that peak is F1, F2, that's F3. These are resonant frequencies of the vocal tract. They're called four-mans, not four-man, four-mans. F-O-R-M-A-N-T-S, four-man, M-A-N-T-S. What is the assumption in this model? I have shown you a model where I have an assumption I have to make. The assumption I have made is that the excitation and the vocal tract system are independent. Excitation does not depend on the vocal tract. Vocal tract does not depend on excitation, which is fine. The second approximation is I am assuming that the vocal tract is fixed for 10 milliseconds. Normally, if you do all the measurement across many people, you will find when you are producing a speech, the shape of the the rate at which the vocal tract changes is about 10 to 20 milliseconds. So every 20 milliseconds, definitely you'll change your vocal tract shape. Otherwise, you'll produce the same sound. Okay. So why can't I move faster than 10 milliseconds? I want to move my vocal tract very faster. Well, you can do digitally, not analog system. Analog system has got all inertia, everything pulled, muscles are pulled. So those muscles cannot be moved faster. You can try to move them a bit slower, but not faster, not too fast. So the range is about 10 to 20 milliseconds. Every 10 to 20 milliseconds, you've got a new set of parameters. When I'm saying a word like hello, it's about 500 milliseconds. Every 10 to 20 milliseconds, I've got three frequencies of vocal tract. First 10 milliseconds, another three frequencies, another three frequencies. And also I want to know whether it's a voiced or unvoiced. I want to know what sort of intensity. All sort of things comes into play. But the main part is every 10 milliseconds is these resonance frequencies are varying for every 10 milliseconds for a voiced or unvoiced. Doesn't matter. They will start to move slightly while you are speaking. So I'm going to look at the speech sounds now. The phonemes, we talked about it, is a smaller segment of speech sounds, and which we call as phoneme, which is for example, dark, up. It's a phoneme, bark, K, all phonemes that's combined together. It's important to realize the phonemes are abstract linguistic units, the smallest sound, and may not be directly observed in speech signal. If you're looking for a phoneme in a speech signal, you may not see it. Phoneme is the abstract sound, like the smallest. So when you produce a speech, you can't say, that's the phoneme 1, that's phoneme 2. No, you can't say that. The linguistic people will be able to translate your sound into phonemes. Your sentence will just take into phonemes. They say this is the phoneme. And also they will be able to say you are not pronouncing this phoneme properly, and they can train you to improve that particular pronunciation. But you can't simply say from that point to that point is phoneme 1. Very hard to say that. There are 40 phonemes in English, 45 phonemes in English. So how do I produce a sound? I have got 45 phonemes learned, and when I want to say a word hello, I pull the phonemes, belongs to the hello, I think it's about five phonemes, put them all and put them in the correct order, and move my vocal tract according to that, and I get a sound. Here is the acoustic waveform. You can see an acoustic waveform. This is time. This is amplitude. This is background. I'm not saying anything. Nothing. Suddenly the waveform goes up and down, and then nothing, and then I'm saying something. So the word I'm saying is it. I'm saying E. E means vocal cord vibrates. That means a lot of volume. E, the whole lot of energy. And here, last sound is T. T sounds means plosive. You build up the pressure and release them. So that's what this is like a building up the energy and then decreasing them. And if I take one frame, what is one frame? Remember I showed you one frame? One frame is 10 milliseconds. I just grab a 10 millisecond frame here, like a 10 millisecond, like I take all the samples from that. It's more than 10 milliseconds, but anyway, I grab that and plot them. When I plot them, this is how the waveform looks like. Here looks, there's the waveform like that, and then dies off, and big waveform, and then dies off, and the big waveform. And if I start to measure this distance, you will find that's the distance of the vocal cord vibration. Immediately I will say, this is a voiced sound, because I see these peaks. So you can see that when the vocal cord vibrates, that excitation hits the vocal tract, and the output waveform is actual pitch is there. And these are due to the vocal tract resonance. These small bumps are. So here's an acoustic waveform. And you can tell me from this waveform which part is voiced, which part is unvoiced. Now take this part and you can say, oh right, here is voiced, I can see peaks and then dies off. So if I look at this part, it's like this, and then it dies off like that, and then goes up, and that's the voiced region. And I go to unvoiced region, like the word is called bush. Ish means unvoiced. You see, there's no energy there, no pattern there, it's random noise, right? But you can see the volume is all, like that's all the height is. And you can see another thing you observe very carefully in waveform, people don't look at them. Do you see, during this time, like when you say, at bush, at U part, is a steady amplitude, here look, equal amplitude. But at the start, when you start B, your vocal tract beginning to excite. So the amplitude is small. So amplitude builds up and steady. And when you finish your sound of BU, it decays. Vocal tract does not vibrate anymore. You can't, this person did not say bush very fast. He said bush. So it goes down, and then you switch your soft switch to unvoiced, and you say S, and you get that out. So you can see how the pattern is. This is called voiced start period and voiced end period. It's starting, start of voicing, end of voicing. This is end of voicing. So it's end of voicing, start of voicing. So I have explained so far speech production, how you produce the speech, what you have to do, and everything very well. Now, I want to look at a speech production model. I want to write some equations. I want to develop a speech production model, and I want to write some equations. That's what I'm after now. Next slide. How do I do that? How do I do model for speech production? Where do I get that model from? I need to develop the vocal tract as a filter, as a digital filter. And then I can do everything what I want. So what I do is I've got a diagram which will show you in the next page. I'll move on to the next page. The diagram consists of excitation, vocal tract, lips, and I decide voiced to unvoiced. So let me go to the next page. You will see. Here is my impulse train generator here, because I've decided I'm going to say a word voice sound, right? Then in the glottis here, as soon as you produce pulses, the glottis is a kind of a low pass filter. It actually shapes the pulse. So the pulse doesn't look like a sharp pulse. You can, that's really ideal. You will find the pulses are shaped like that. But still the periodicity is maintained, still the period. And then its amplitude is adjusted by a volume controller. Similarly, for random noise, you got a box here which creates random noise. Its amplitude is adjusted. Then this switch decides where to go, which one to, and then you go to vocal tract. Vocal tract has got a transfer function, which is a digital filter, which has got a resonant frequency. Resonant frequency means what? If you take a digital filter, it must have a transfer function of 1 over 1 plus V1 set to the minus 1 plus V2 set to the minus 2. You've done properly. And you can analyze, and this filter has got a resonant filter. It will give you one resonance frequency. So if you've got 3 resonance frequencies, you must have 6th order filter. 1 second order give you 1 resonance, another resonance, and 6th order filter minimum you need here, but normally you need more than that. After that, you've got a lips model. What is a lips model or radiation model? Because depends on the sound. If you're going to say a sound like O, you're going to have a different position, different lips. So lip radiation model has been developed, and you need to put them in. So by the time you're producing a sound here, your excitation started here, has gone through this path, shaped and everything, and comes there. And we need to write equations for that. Or you take the other part, which is this part, go through this, and produce another sound like that. That's unvoiced sound. So you need to write the equation for this. That's what we are trying. So this is the model for discrete time model for speech production. So what is an excitation process? Excitation is here is an impulse. Impulse, you know, every one of them know, impulse can be represented by delta. Delta n is an impulse. And if you want many impulses, you say En is equal to delta, here's the equation, n p n minus pk. P is the pitch period. So you're saying your impulse is delayed by the pitch period. 1 period, 2 periods, 3 periods. So in this equation, we'll give you an impulse there, the distance between them are p. That's what the equation is for, impulse response. For unvoiced sound, you say En is my random noise. You produce random noise from a computer. And this is, you write a program to generate those two. What's the excitation source then? So this is the equation that we are going to have. This is what we want. This is the equation I wrote. Is that clear? I'm sure it's clear for you. You know, relook at them, okay? Then I want to translate this into set transform because it's a discrete system. So I take the set transform of that. And if you write the set transform equation, which you know family already, you have run signal processing, you can show it's a power geometric series. If you expand that, that gives you an equation 1 over 1 minus set to the minus p is your excitation equation. Very simple equation there. So I got one model, right, done. Now you can say, if that's the case, fine. We want to do pulse shaping. As I said to you, in the glottis, there's a low pass filter. It does shape of these pulses. And this is only used for voice speech. For unvoiced speech, there's no glottis opening. Glottis does not come into play. The vocal tract is held apart. So the air just comes through. Whereas for voice sounds, the vocal cord vibrates and the glottis area is measured as a low pass filter. So people have worked out and shown that glottal model, that means excitation going through the glottal model, gives you a transfer function of that. And this is approximately equal to 1. T is your sampling frequency at which you are. And you will find this works out to be, that's your transfer function. What does the transfer function tells you? Basically, you are saying GSAT is equal to 1 over 1 minus set to the minus 1 multiplied by 1 over 1 minus set to the minus 1. So I could say this is, yes, this is 210. That means it's a first order filter, a low pass filter cascaded. So it's a second order low pass filter I get. And what happens is the glottis does not come into play for unvoiced sound. So unvoiced sound G set will become equal to 1. So we have said that we have got an equation for excitation, we have got an equation for a glottal model. So we got those two. The next one is vocal tract model. So you will find glottal pulse after shaping. I mean, originally you got pulses like that. After shaping, they look like this. These are still pulses, but shaped pulses. And the frequency spectrum, when you plot it, is just like that. It keeps very fast. So it has got all these frequencies are kept. This decays very quickly. That's the excitation part. If you plot the frequency spectrum of those waveforms, and if you take one glottal pulse, which is like that, and if you plot the frequency spectrum, you can see it's a low pass filter. That's frequency, that's amplitude, and you can see it's a low pass filter. Dying off. So the low frequencies are here. High frequencies are suppressed, so it's a low pass filter. You can prove anything using MATLAB now. And here's an exercise where you have been given GN is a glottal model equation, and you have to write a MATLAB code to plot the pulse and its spectrum. So you should try this out in your lab to get an idea because what is glottal, what is the glottal spectrum. Now you can say excitation process. How does it work out, all these things? You could say I have got excitation here, followed by glottis. So you can say excitation followed by glottis, and then I have to multiply by a gain factor. So in time domain, if this is En, is input En, then you can say that if this is, that whole thing is now referred as En here. We have an equation there. And if this impulse response is Gn, you could say what's coming out here is, these two convolve to multiply by A. So En convolve with Gn, so multiplication. This is convolution. Or, if you take the set transformers, convolution becomes as multiplication here. Look. So it's easy. When you're doing modeling, you do it in set transform and then take the inverse set transform, rather than doing everything in. So, now I can say, from now onwards, here is my voice path, Xn is my output, and here is my unvoiced path, Xn is my output again. Depends on voice to unvoiced, this volume is controlled. For voice, AB is kind of bigger. For unvoiced, it will be lower. Vocal tract. Now you've got a problem with vocal tract. How are we going to model? We've got all those this done. Where does the vocal tract come into play? You've got a white noise going to the vocal tract. Impulse going to the vocal tract. Vocal tract, if you take section, this is section 1, section 2, section 3, section 4, you will find there are different shapes. You can see different shapes. And through that shape, you get your speech coming out. This different shape contributes to resonant frequencies. Okay? And you can look at, and we can show that tau is the time taken for the wave to propagate through the single section, one small section of the vocal tract. There's many sections there, 1, 2, 3, like that for vocal tract. For one section, it takes tau is the time taken, and it has been shown before that for a discrete system, we have been shown that if you want to sample based on that is 1/2 tau is our sampling frequency. And we can relate that to the number of sections you have, and you will find that if L is the length of your vocal tract and C is the velocity of the sound, N is the number of tubes or sections, we can write this equation. This has been proved before. I wouldn't spend a lot of time trying to prove this, but if you're interested, you can read Rabina's book. They have got a section on that. Now we are into a place where we want to find out form and frequencies of the vocal tract. I want to write an equation for the vocal tract. I have to do that next. I have got equation for excitation, equation for glottis, and then gain control, which is the AV control. Then I have vocal tract. So here, I'm here. Now I want to get equation for that. Then I want to get equation for the lips. So now you have to ask, what is the transfer function of a glottal model? It's a low-pass filter, 2 first-order low-pass filter. Okay? I have already mentioned about form and frequencies before. It's the resonant frequencies are the form and frequencies, and it exhibits normally resonance 1 formant per 1 kilohertz. And for voice speech, the formant frequencies is successfully larger than the magnitude of the higher frequencies because your curve looks like this. So this is very much higher than this one. For unvoiced, it will be the other way around. This much high frequency is higher than, amplitude is higher than the low frequency. So it's really in that particular format. So I'm going to show you a voice speech. Here is a voice speech I selected as the pitch period. I take a Fourier transform of that, fast Fourier transform, and produce the magnitude if you want. And you can see here, what is this? This is your first formant, frequency at about 700 hertz or 800 hertz. Second format at about 1700 hertz. And the third format around 3200 hertz. So you can see this amplitude is higher than that. That's the way you will find for voice speech most of the time. And you can see here, this is like whole data. This data is analyzed, right? You don't analyze frame small section, like the whole frame, which is about 10 to 20 milliseconds. So if you're doing frame processing like that, speech, you divide, it doesn't matter where you start, you say, right, that's my first frame, that's my second frame, frame 1, 2, that's my third frame, and you can look at this form and frequency. For the next frame, it could be like that, it could be like this, it could be like this, you don't know. For the next frame, it could be slightly this way, and then this way. So it can be. So every frame as you speak, these vocal tract changes. These changes are being tracked by the brain to determine what's coming out. These frequencies are determined by the brain. Exactly what is coming out, and it knows then from those one, it belongs to this particular phony or belongs to this particular class. Okay? Here is an unvoiced sound. It's important to know there's no pattern. There's a very noisy sound. If I take the Fourier transform of that, you can see here, this is, well, for this particular case, this is higher, and this is lower, and this is lower, like higher. In reality, if it's a perfect sound, you will find this is higher, and this is lower, and then this is very much lower. That would be the correct one. But I just wanted to pick up a frame of, which is not really unvoiced, is not really voiced, but it's kind of in between, can show that particular pattern. Can confuse sometimes. Here is my vocal tract now. What is the vocal tract? I have got a second order filter, 3 of them at least, because I want 3 resonances. Normally you get 4, 8th order filter. So we don't know how many orders. We just say to them, okay, if you want to go for vocal tract modeling, you go for all-pole filter. Everything is pole. That means you only have poles at the denominator. And the vocal tract transfer function is 1 second order multiplied by many orders. This is multiplication sign. That is multiplication sign. And k has as many you want. If you expand this, this will become as a polynomial. And if you say I've got 4 sections, so 6 sections, then the P becomes 4 sections mean 4 SECTION. 4 sections mean 4 times of 2, which is equal to 8. So P will become 8. 8th order equation, 8th order filter. Okay? So it's all pole. There's no zeros on the top. There's nothing here. So it's all pole filter. Now you are into modeling. Okay, you can start from here. I've got that equation. I got that equation. I got that. I got equation for that. I can have an equation for that. Then I can write an equation for speech output. So if you do all in time domain, you have everything. That output, that one, is convolution of this with convolution of Gn. There you are. Multiply by that. Then that one, whatever coming here, is then convolved with this one. You convolve that, and that will be your output here. And then if you know this model, you convolve this one with that, and that will be your speech output. And if you work it out, it will eventually become a convolution of that with that with that. So 3 cascaded body, so they all will be convolved. But we don't want to look at convolution in time domain, we look at frequency domain. And in that domain, you will find all these convolution turn into multiplication. So if you know the transfer function of the glottal and the vocal tract and the radiation function, you multiply all these 3 by the gain factor, you get transfer function SZ divided by EZ. So these are all assumptions. We don't know these values yet. We only have speech. So we are, from understanding the speech, we are trying to model backwards and say, this is the model we have. And in an exercise, I want you to try this out. What you have to show when A is less than 1. This first order 0. This is a 0. 0 means it's at, say for example, 1 minus A naught, that is a minus 1, over 1 minus A B naught, that's a minus 1. This is called a 0. This is called a pole. We only have 0. We can show, if A is very much less than 1, which you should try, very important, that we can show this can be done by that equation. And then we can say if A is less than 1, every 0 can be approximated by 2 poles. You don't need many, by 2 poles. So every 0 you have got 2 poles. So if you have got a transfer function with 1 0, you say, I can put 2 poles for that. If I got 2 zeros, I got 4 poles. So we can do that. You might wonder, why am I doing this? Well, we do need that. So far, we talked about vocal tract. We haven't talked about nasal tract, so we have to talk about that in a minute. So, next question is a lip radiation model. People have worked out the model. It's a differentiator. It's a high-pass filter. And the lip radiation model is like that. And this is a high-pass filter. If you look at R theta is the frequency, theta, digital frequency. If you plot this, it will be like that. Oh, well, it will be like this. So it suppresses the low frequency and enhances the high frequency. It's a high-pass filter. You should use this MATLAB and try to program that and see. That's your transfer function of your lip radiation model. And if you plot it, this is what you get. This is your frequency response. That's frequency. Now the question is right. Okay, we have done all these equations. Let's put them together. Here is my excitation. Here's my vocal tract model. Here's my lip radiation model. Let me put them all together. And my excitation at that point. So output equal to that multiplied by that multiplied by that. So you keep multiplying all of those. Now glottal model is that, and this would be, I think what's missing here is, a glottal model is missing here. GSAT is not drawn here. And you can say that's inside. So these two can be inside. So eventually you have a transfer function, SZ over EZ, E will be at that point, this will be like excitation and glottal, so this will become G. So you say S sat over G sat, so E sat is equal to that multiplied by that multiplied by that. That's what you have. Plus A is the gain. I didn't put the gain there. So that's the model for overall speech production model. Next, overall transfer function. Now let's write the equation for this model. All voiced model I'm talking about. So here's the overall transfer function. I'm now putting in G sat is the second order low pass filter. V sat vocal tract is the pth order filter. Depends on how many resonances you want. Radiation is a differentiator, 1 minus 0.98 set to the minus 1. That's a kind of non-ideal. Or you can say 1 minus 0 minus, that's the minus. They're all perfect differentiator. So I got a perfect differentiator here, and you will find when we are producing a speech, this differentiator and the glottis low pass filter here, they'll cancel out. That will cancel out with one of those. And that's what you'll end up. And then your transfer function will become that will now multiply inside here, and this will become P plus 1. You can see here now. So your transfer function is, if P was 8, now you become P equal to 9. Right? So depends on how many resonances you want, you determine the P. So that's your transfer function of a voiced speech production model. Now you can do the overall transfer function. What I have done here is, I'm looking at unvoiced speech. For unvoiced speech, glottal is equal to 1. Remember, there's no glottis. It's open. And this is there. And then you've got R sat. Now the question you're going to ask is, what is this? P is okay. Where's this 2L? What happened for unvoiced speech, which is not on the, it will be on the lecture note, it's missing here, transfer function. What happened for the unvoiced speech is, the nasal tract comes into play, and you have got zeros. You've got a lot of zeros. So unvoiced speech is transfer function S sat over E sat is equal to, you will have, G sat is 1, you'll have A, U, V. Then the vocal tract would have 0 on the top and a pole as well, both. And then R sat, which we know is only a single order. The problem is that because of the nasal tract, we have got zeros in the model. And just look up on the lecture notes on the web, you will find that one transfer function is missing here. That's what happened. And this 0, I have already showed you, every single 0 can be represented by 2 poles. So if I have L zeros, if I have got L zeros altogether, if I got L zeros, I've got 2L poles. So that's how it happens. Already there's the P poles available, and if you've got zeros, you translate them into 2L poles. And you've got another 0 here. You can put that also into another 2 poles. So eventually, for voice speech, you need P poles. For unvoiced speech, you need P plus 2L plus another 2. That many poles you want. So now you may ask me, why am I doing that? Because I want to have a single transfer function without a 0. Then I can manipulate things later. So now I've done is that made a single transfer function. It doesn't matter voiced or unvoiced, but this is my transfer function. I could now say if P is 8 for a voiced, for unvoiced it might end up as 12. So if I model my vocal tract by 12-pole transfer function, it will cover for me voiced as well as unvoiced. I don't need anything more than that. So that's the idea of all this approximation. I don't want any 0 in my transfer function, even though there are zeros. So whether you produce nasal sound or vocal sound or unvoiced sound, you've got a one single transfer function, which is the next slide, I think, will give you. Here is the one transfer function, which is telling you Q is the number of poles. So by doing a lot of analysis, a lot of speech and a lot of sound, we found that P equal to 12 is more than enough to represent most of the sounds that we to model using this equation. So what are AK? AK are the digital filter coefficients of the vocal tract. Now we are going to say basically excitation, something coming out. In between, I've compressed everything into one transfer function, one single block, which is my vocal tract filter. Everything is pushed inside the vocal tract. Just one filter now we have. One filter mean which has got many resonances. Now Q is 12. So most of the speech analysis, vocal tract is modeled by 12-pole filters. Q is 12-pole filters. So you will find 8 of the poles contribute to resonance. Remaining 4 shapes the spectrum. They're not complex. So if you want resonance, your filter, a second order filter, 1 over 1 plus B1 set to the minus 1 plus B2 set to the minus 2. It's a second order filter. If this have to have a resonance peak like that, this must be complex coefficient. Sorry, they should have complex roots. You have learned that in signal processing, so I don't need to go through that. So the use of vocal tract. Where do we use this vocal tract model? Right. Basically, in speech processing, we normally analyze the speech every 10 to 30 milliseconds, and we use this model for various applications. One of the famous applications you'll be using linear predictive coding. Using this model, using the speech, we have a model now. We've got an equation, but unknown. One unknown is a coefficient. We don't know, but we know the speech. From the speech, we will do a prediction, and we will know what coefficient we have to use for the vocal tract. So we can actually predict the vocal tract shape and position and resonance frequency from the speech. We will do that later on, which is called the linear predictive coding, chapter 3. We'll come to that later. So if you ask me, what have I done? I have set up a model for you. I have set up a voiced model and unvoiced. I've combined all of them into single excitation, and I've combined all of them into nasal, everything into one vocal tract model. And if you draw it, which is a old-pole model. Now you may ask me, why do you want to have old-pole model? Old-pole models are easy to manipulate and also easy to do calculation on that. If you have zeros, then things become a bit complicated. So refine this model. I have refined the model, removing everything, and I have now only these two coming in, and G, and that's my vocal tract model. And this is P is equal to 12 now. That will cover virtually everything for me. So going back to the vocal tract model, what I can do now is, if this is my speech output, and this is my input UN, this is my gain, whether voice to unvoiced, it doesn't matter. Q is my number of poles. I can actually write an equation, cross-multiplying this way and that way, taking inverse set transform. You take inverse set transform, inverse set transform. You will get the original speech equal to that plus that. What does that tell you? This tells you I can have my current speech sample, current value of the speech I produce is equal to a constant multiplied by the previous values of the speech. So if I know the previous values of the speech and multiply by the correct constant and add the excitation here, if I do that, I know what speech is going to come. So from the past sample, I can actually tell you what the current sample is going to be. That's what this equation tells you. Current sample is equal to the coefficients multiplied by past samples of speech plus the excitation modified by the gain. And that's very important. That's in time domain. That's time. That's in that domain of frequency domain. You must be able to interpret this equation. So you've got an exercise here, and you've been given a waveform, and you want to go through the waveform and locate various things in it, and I'm going to leave that as an exercise. Here's a waveform. You can actually locate where the voice speech starts, where if the waveform word is called cattle, and try to analyze and see what you have. And then later you can ask in the class. Oh, I put the answer as well. Sorry, I shouldn't have, but I have the answer. So you can check them all. Okay? Don't look at the answer first and find out where the lowest pitch occurs, and don't check the answer. Try your way first, and then you can put it in. You can check it then. This is another exercise. This is another one I have given you. I've got a glottal model, and you need to take the Fourier transform of the glottal model and plot the Fitch's response and magnitude response. Again, it's a MATLAB exercise to give you an idea how you do this. Now, this example, I'm not going to go through. The example is there for you. I think you should be able to figure out the example. I have given you an example where the pressure at the lip is equal to the resistance or impedance multiplied by the lift volume velocity. And these are radiation impedance, these are radiation resistance, radiation inductance. Somebody is modeling the lip radiation model. And using this equation, you have been asked to show that by doing all of this using bilinear transform, you have to show first R set radiation model is given by one particular equation, and the equations are all explained there. I think the solutions are all given there. So I'm not going to go through them. You go through the equation one at a time, and the solution is worked out. And I want you to go through this exercise step by step and understand, and then you can ask me. Because this particular exercise is very simple. It's basic DSP. So I didn't want to run through this exercise. If you do have problems, you can ask me. All I am doing is I have been given, if you go back here, I have been given this as my transfer function, which is analog. And from, if you want to go from analog to digital, use bilinear transform. So if you do bilinear transformation, which you do in the next page, if you do bilinear transformation, here is the bilinear transformation, 2 over c. That's bilinear transformation, okay? And once you do the bilinear transformation, bilinear transformation, you get your equation, this one. And this is become as 1, 0 you have, and also you got a 1, 4. And all these values are given. So the radiation pattern has got a equation. And you can then write from that equation corresponding difference equation you have been asked to do. And then you have been asked to find out location of the pole and location of the 0. Very simple. In the right, you go back and say make this equal to 0. You can look, sorry. Everything is going wrong. Must be system is getting tired as well as I'm getting tired as well. Okay, so you make this into 0, you get your zeros, and you make this part equal to 0, you get your poles. Or pole, really. So they are the two things. Once you've done that, you got the pole and 0 answer. And then you put in all the values and you can calculate the resistance and everything. Okay? And you eventually show that is by neglecting the pole, you are proving that your radiation function is a differentiator. That's what you're trying to do. In this question, by doing this approximation, you're showing your lip radiation model is a differentiator. Another example of glottal pulse, and another example that you want to plot this. And in this case, the important part is that you have been asked to find the transform first, and then you asked to find S theta or G theta. So G theta is the Fourier transform or digital Fourier transform. Okay? So you go through this exercise, and you've been told that eventually find the value of A in order to give you a particular frequency response of 60 dB. And you've been given this particular transfer function as well. So it's very, very simple, this question again. Just go through them step by step. You start with your equation, and this is your transfer function for that particular equation, or set transform. Then this is given, you apply this, and then from that, you can now say your function G sat, which is Gn you had, equal to a to the power n. Now you got a to the power n. Using this equation, you can show this is your transfer function of your g set. If you don't understand, you can ask us. That's very, very simple. And then, once you know, you then take g theta and substitute all the values and find out the modulus value and then plot them. You can use MATLAB, and which you use MATLAB if you want without all this process. FREQZ, fix that plot, and which will give you frequency in one go. You don't need to do all these now. What I have done. Okay. So basically, the C part then is find out your magnitude at 0, find out the magnitude at pi from the equation, then take the 20 log A minus B to divide them, which is equal to 60 dB given. You just simplify this and find the value of A, and when you work out, A becomes 0.9387. That's your final part. So that comes to a conclusion of that particular chapter. I hope you have understood the chapter. And if you find it difficult, something you don't follow, please ask in the tutorial class or the lab class when you go next time. Don't leave it late. And I can be available, or the tutors will be able to help you on this matter. And just a matter of going through, tell us about the CD, what you're saying. If you think you want more about it, we can help you. Okay? All right then.
I'll be happy to